Okay, good morning to everyone. Today we are going to see about the OTTO cycle. Right? Okay, right. So already we discussed about the concepts of gas power cycles. In gas power cycles, we have a n number of cycles. We are going to concentrate only on four various cycles: one is OTTO cycle, diesel cycle, fuel cycle, and one more thing is a Brayton cycle. So today we are going to see about the OTTO cycle and why the name we are given as OTTO means actually the scientist name is OTTO, right? Who derived the OTTO cycle, which is operated especially for a petrol engine, right? So now we are going to derive the efficiency of an OTTO cycle and what is the mean effective pressure for an OTTO cycle and work done of an OTTO cycle. First, we are going to see how can you derive the efficiency of an OTTO cycle. So before that, we should know what are the process considering in an OTTO cycle. Okay, so, the first process is actually we are considering a four various process. In that, two is a isentropic process. Rest will be a constant volume process. Okay, the first process is a reversible adiabatic compression process, and second one is a reversible constant volume process where heat is added. Okay, so actually heat addition takes place where the process is constant volume. And third process is a reversible adiabatic expansion process. And fourth one is a reversible constant volume where heat is rejected. Right? So actually these are the four various processes considered in the OTTO cycle. Two is a adiabatic process, another two is a constant volume process. So actually the reversible adiabatic process, otherwise we can say as isentropic process. Okay, already we know that maybe studied in thermodynamic itself. Reversible adiabatic, otherwise we can say as isentropic process. Okay, right. So these are the various process considering an OTTO cycle. Already you know that what is meant by compression and expansion. Uh, in the case of a compression, there is a changes in the volume and process. Likewise, in expansion process also, right? So we will see how what are the parameters going to changes during these various kind of process. Okay, so now we will plot the PV diagram and PV diagram of an OTTO cycle, right? PV diagram of an OTTO cycle. So actually here we are considering a four various process. First one is for example, started here. Okay, the first process is compression process right? So compression mean nothing but the volume get decreased, right? During compression, pressure is increased. So from this position, right, initially the pressure may be considered here, right? So pressure is increased from this position to this position. Here may be considering as a P2, right? So compression, we know that volume get decreased, right? From this position to this position, V1 to V2. So pressure also increased. So there is a reversible adiabatic compression process. So we can give a name as 1 to 2, right? And next process is a heat addition at a constant volume. So constant volume means we can maintain the volume as constant, right? So this is between 2 and 3 constant volume process. Here heat is supplied. Heat is supplied. And another process is here again constant reversible adiabatic expansion process. So expansion means we know that the parameter of volume get increased and pressure get decreased. See here from this position, actually from the parameter name 4 and 3, pressure actually. So this is the maximum pressure we can say as a P3. From position P2, it decreases to 4. The pressure actually get decreased in the expansion process and volume also increased. Okay, so here volume increased. And another process is here reversible constant volume process. So you can plot like this constant volume. Okay, and this is so where heat is rejected. So heat is rejected during this process. So the process 1 and 2 and 3 and 4 we are saying is a adiabatic process. Already we know that adiabatic process equation is PV power gamma equal to C. Already we studied in the previous semester thermodynamics itself, right? Okay, and see, so already we discussed about the clearance volume. Okay, what is clearance volume? It is denoted by the symbol V suffix C. Clearance volume is nothing but some amount of, sorry, there is a some amount of volume is occupied, right? Some amount of volume is occupied at the while the piston travels towards the top of the cylinder, right? Some amount of volume is occupied. So that means a small gap may be occupied. So this is we can say as a clearance volume. Clearance volume. So the distance traveled between from V1 to V2, that is the distance traveled by the piston, right? We can say as a stroke volume. So stroke volume is nothing but V1 minus V2. Okay, the whole thing we can say as total volume, right? So I hope all of you clear, right? How can you plot the PV diagram of an Otto cycle based on your process? Simply I plotted here, okay? And during the compression, already we know that what is need to work done on the system and work done by the system. Work done on the system means nothing but some amount of work is supplied to the system from external, right? For operating and compression. That is if you want to increase the range of pressure, if you want to compress the system means definitely we need to apply some amount of energy from outside. So that is work done on the system here. Okay, so this is work done on the system and process here which is work done by the system. During expansion, there is no need to apply any amount of energy. So automatically, because of higher pressure, it travels towards the another parameter, right? So likewise, we need to plot a TS diagram also. Right? So the first process already we know that which is a reversible adiabatic compression process. In that process, pressure is getting increased. Already we know that pressure is directly proportional to temperature. So definitely, if your pressure is increased, I mean temperature also increased, right? 1 to 2. And if the process is reversible adiabatic means always the entropy is constant. This is discussed in previous thermodynamics itself. Please be reminded, for a reversible adiabatic process, entropy must be constant, so that I can plot like this, maintaining the entropy as a constant from position 1 to 2, but pressure increased, so the temperature also increased from this position to this position, T1, T2. Temperature is increased, right? And second process, constant volume heat is added to the system. If heat is continuously added to the system, means definitely temperature also getting increased. So you have to plot like this, right? So from this question we can say as T3, okay? And next is a expansion process, temperature getting decreased because of pressure decreased, and final process is a constant volume heat rejection. Heat rejection means temperature is decreased, yeah, from this position to this position, temperature decreased. Because of adiabatic process, here you can maintaining the entropy is a constant. Okay? So here heat addition, here heat rejection. I hope all of it clear. How can you plot the PV and TS diagram, right? So this is TS diagram, right? Okay. So now see, how can we derive an efficiency of an OTTO cycle? So generally we know that efficiency is in a defined as ratio of work done to the heat supplied. Okay. So net work done, which is nothing but difference of heat supplied and heat rejection, right? So this is general formula. So by that we can derive an efficiency of an OTTO cycle. Okay. So already we know that the general formula for heat is nothing but mc del T. So if you write for a heat supplied mean, actually which takes place at a constant volume, C is nothing but specific heat at constant volume. Because of constant volume process used here, the temperature difference takes place, heat supplied actually takes place 2 and 3. So we can say T3 minus T2. Likewise, this is our equation number 1. Likewise, for a heat rejection, so here also the volume is constant process. MCV, the rejection takes place between, that means uh, between 4 and 1, right? So this is equation number 2. Clear? Okay. Then Now go to the derivation. Efficiency equal to heat supplied minus heat rejection divided by heat supplied. We know just substitute the equation number 1 and 2 here. Instead of heat supplied, we can use mcv del T3, sorry, T3 minus T2 divided by minus of, and heat rejection is mcv T4 minus T1, okay, whole divided by again heat supplied mcv T3 minus T2, right? So simply commonly taking outside the mcv, right? mcv, if taking commonly outside means the rest will be a T3 minus T2 minus of T4 minus T1, right, divided by mcv T3 minus T2. So the mcv and mcv get cancelled here, okay, and next step remaining parameter is here T3 minus T2 minus of T4 minus T1 divided by T3 minus T2. So here also, right, T3 minus T2 and T3 minus T2 get cancelled, right? See, so get cancelled. So we can say as a 1 minus T4 minus T1 divided by T3 minus T2. Look clear. So because of same numerator and denominator, so get cancelled. So this is equation number 3. Okay. So this is a basic formula. If the temperature term is given means in a problem, you can use this formula for an measuring the efficiency of an OTTO cycle, right? Okay. So again, we need to go for a simplify the equation, just replacing the temperature term. You can go for a further extension, right? Already we discussed what is meant by compression ratio, which is denoted by the symbol R, compression ratio or suffix C, and one more thing is a compression rate, sorry, expansion ratio, that is denoted by the symbol or suffix E. So the compression ratio is nothing but the ratio of V1 divided by V2, right? So please you can refer from the diagram also. V1 is nothing but total cylinder, okay, and V2 is nothing but clearance volume. So the compression ratio is nothing but ratio of total cylinder volume to the clearance volume. So that is the compression ratio, okay, and expansion ratio, expansion process actually takes place between 3 and 4, right? So where volume at 4 is higher than V3, so we can use the term like that, V4 divided by V3, which is the expansion ratio, okay. So simply both the term we can say as R, and this is also denoted as right. So simply we can use as R for a compression ratio and expansion ratio. So then just we can form a certain relations, okay. So for example, first if you consider the relation process between 1 and 2. So actually what is the process between 1 and 2? 1 and 2 is nothing but is a reversible adiabatic process, otherwise you can say as a isentropic process, right? We know that the basic equation for a adiabatic process is nothing but PV power gamma equal to C, right? This is the general equation of a adiabatic. So here we are considering a process 1 and 2. So we can say P1 V1 power gamma equal to P2 V2 power gamma, right or not? Because of a constant between the process 1 and 2, which is a reversible adiabatic process, we can rewrite this equation like this. Okay, fine. I hope all of you clear. Just we can form a equation in terms of temperature, because here we need to substitute inside of temperature term either for a T1, T2 or T3, T4, whatever maybe. So from this we can form the equation as in terms of temperature. So we know that the general gas equation is PV by T equal to C, right? PV divided by C. So instead of pressure, okay, instead of pressure here, we can substitute from this equation, right? Instead of pressure, PV equal to T divided by C, right? So C, instead of P1, we can use T1 divided by, sorry, not a C here, which is B, right? P equal to T by V. So T1 divided by V1 into V1 power gamma equal to, so likewise instead of P2 we can substitute T2 divided by V2 into V2 power gamma. So here T1 equal to, we can, sorry, T1 into V1 gamma minus 1, right? So actually from denominator move on to the numerator means we can say as, which is nothing but minus 1. So I can simply write like this, and T2 into V2 power gamma minus 1, right? So from this we can form a equation like this: T2 equal to T1 into V1 divided by V2 power gamma minus 1. So instead of V1 divided by V2, we can substitute R. So previous cases we see, which is nothing but compression ratio, total cylinder volume to the clearance volume, right? So T2 equal to T1 into R power gamma minus 1, right? Since R is nothing but V1 divided by V2, that is total volume cylinder to the clearance volume, so that we can replace instead of V1 by V2 as R. So this is equation number 4. So this is one type of equation. We can replace instead of T2 in the efficiency equation. So likewise, you have to considering the process 3 and 4. So actually 3 and 4, which is also a reversible adiabatic process. So similarly, if you substitute this is adiabatic process, so that if you consider the process between 3 and 4, because of adiabatic process, we can say PV power gamma equal to constant. So we can write like this, right? And again, instead of P, we can substitute T divided by V. So finally, we can form the equation like this instead of, sorry, in terms of temperature as T3, sorry, T3 equal to T4 into R power gamma minus 1. So which is equation number 5. So if you have doubt means please replace the pressure terms, and finally we get the term like this: T3 equal to T4 into R power gamma minus 1. Okay, so here actually the equation form like this actually. R equal to V4 divided by V3. We know that V4 by V3 is nothing but expansion ratio. So simply we can use the term R, okay, so that we can getting the same equation. So please use this also. Okay, now you can substitute the equation number 4 and 5 in equation number 3. Okay, so in equation number 3, instead of T2 and T4, we can substitute the equation 4 and 5. So let's see now. One minus, actually T4, sorry, T4 minus T1 divided by T3 minus T2, right? So 1 minus, instead of T4, you can keep it as a T4. Instead of T1, there is no need change. You can keep the same thing. Instead of T3, we can use T4 into or power gamma minus 1, and instead of T2, you can use the equation number 4, T1 into or power gamma minus 1, right? Okay, then again 1 minus, you can use the same thing, T4 divided by T1. So here commonly taking outside or power, sorry, or power gamma minus 1 into T4 minus T1, because of the same term or power gamma minus we can take in commonly outside, the T4 minus T4, the term get cancelled. Okay, then remaining term is here 1 minus 1 divided by or power gamma minus 1. So this is the efficiency of an OTTO cycle simplest form, right? Just a thing. So this is, you can take it as the equation number 6. So this is the efficiency of an OTTO cycle formula, right? If the compression ratio directly given in our problem means, simply you can take those formula 1 minus 1 divided by r power 1 minus 1, you get the efficiency, right? So if the R value getting increased, right, what will happen? Definitely the efficiency of an OTTO cycle also getting increased, right? So for a petrol engine, actually the maximum compression ratio may be up to 8, right? So already I told in the section starting itself, right? In an OTTO cycle, we are going to derive an what is the efficiency of an OTTO cycle, and second one is the mean effective pressure, and one more thing is the work done. So the first part is finished, that is the efficiency of an OTTO cycle, and next we are going to see work done calculation. Okay, right. So the work done calculation is nothing but, already know that work done net work done is nothing but heat supplied, just a minute. nothing but heat supplied and the difference between heat supplied and heat rejection, right? So actually the work done takes place, actually we discussed about the two various types of work done. One is a work done on the system, another one is a work done by the system, right? So work done on the system is actually takes place during the compression process. Because of compression, definitely we need to apply some amount of external energy, so that we are saying is a work done on. So for a expansion, there is no need of any energy, because already we have a higher amount of pressure. So because of expansion pressure, the higher pressure comes down, right? Without applying any amount of external energy, right? So that means actually we're getting some amount of power in an IC engine during the expansion process. Actually, we are saying it's a power stroke, right? After air fuel mixture get burnt, some amount of power is generated, right? That means by the system means some amount of power is or work is generated by the system, and that is the work done by the system, right? On the system means we need to apply some amount of external energy from outside. Okay, so that is the thing. So here you have to consider work done by the system to work done on the system, right? So this is a one type of thing, and we can say like this also, work done by the system too. That means some output and this is input. So work done by the system actually takes place in the expansion process. Here you have to considering a polytropic process. What is the work done for an polytropic process? So the formula is, we can say as a P3 V3 minus P4 V4 divided by gamma minus 1, right? So already we discussed, you studied in the thermodynamics itself. Please refer that. Okay, work done for a polytropic process, and work done for a on the system, it takes place between the process 1 and 2. So we can give the formula as P2 V2 minus P1 V1 divided by gamma minus 1. Okay, so please refer the polytropic process for an work done formula. So based on that, I am giving here the expansion process actually takes place between 3 and 4, so that I giving the number as 3 and 4, and on the system takes place between 2 and 1. That is a compression process, so that I give you a formula like that. Okay, then from here, so here you are introducing another team. See, already we know that the basic formula for an adiabatic process is the PV power gamma equal to constant. So for example, here considering the process 3 and 4, actually 3 and 4 is a adiabatic process, so that we can write like this: PV VV 3 gamma equal to P4 V4 power gamma. Okay, so simply we can keep like this: P4 V4 equal to P4 divided by V3 power gamma. So V4 by V3 is nothing but, already we know that this expansion ratio, the symbol is we can use as R. So instead of P3 by P4, we can use R power gamma. Okay, right. So similarly, if you considering the process, uh, so already derivative P3 by P4 equal to R power gamma. So just refer the PV diagram. Since from the PV diagram, see, from PV diagram, so actually P3 equal to from the PV diagram, actually P3 equal to P2, right? P3 equal to P2 because of constant process. Likewise, P4 equal to P1 because of constant volume process, right? 4 and 1 and 3 and 2 are equal, right? So please be reminded. So instead of P3 equal to P2, P4 equal to P1, right? So from the PV diagram, so from that we just you can rearrange the equation P3 divided by P2 equal to P4 divided by P1 equal to, simply we can say as here you are introduced the new term or suffix P, which is nothing but pressure ratio. Okay. So I hope all of you get clear. How can you form this equation P3 by P4? So from using the PV diagram, P3 is nothing but because of constant volume process, 3 and 2 are equal and 4 and 1 are equal. Just to rearrange the equation means you are introducing the term that is nothing but pressure ratio. The pressure ratio is nothing but ratio of the pressure at the point 3 and 2, P3 by P2, else we can say as a P4 divided by P1. Okay, right. So then, therefore, now simply you can use in the work done calculation, work done equal to, so see here. So so you can give a equation number for this one. So already we are given the equation number 6, I think. So you can give a name as 7. So from the equation 7, you can take in commonly outside. In numerator, we are having a gamma minus 1. So you can simply take an outside. Okay. And in simply taking outside PV for the simplification process. Okay. Taking commonly outside P4, V4 into, so P3, V3 divided by P4, V4. Am I right? Minus of 1. Okay, right? So from equation 7, simply I am taking commonly outside the numerator term, gamma minus 1. So the rest will be a P3, V3 minus P4, V4 minus P2, V2 minus P1, V1. Again, I am taking commonly outside P4, V4 from the first term. Okay, from here. Taking commonly outside P4 and V4, so that I can write the equation like this. And again, here I am taking commonly outside as a P1, V1. So minus of taking common outside P1. So it's for only for a simplify the equation. So P2 V2 divided by P1 V1 minus of 1. Okay. And again, just you can follow the, sorry, keep the same thing. P4 V4, and here we can write like this: P3 divided by V4 into V4 divided by V3. V4 divided by V3 is nothing but expansion ratio, that is the symbol as here or. So actually here is a V3 by V4, so that we can say as 1 divided by or. Okay, since or equal to V4 by V3, so actually here is a V3 by V4, so that I can write like this. Okay, and minus of, again you can keep the same thing, P1 V1. Here we can write like this: P2 divided by P1 And again, actually the compression ratio is nothing but V1 by V2, but here is a V2 by V1, so I can write like this, right? So R is V1 by V2, so here is a V2 by V1, so I can write as a 1 by R minus of 1. So again, gamma minus 1, you can use the same thing. P3 divided by R into P4 minus of 1. So here also we can change the term. Actually, from the PV diagram, V1 equal to V4, right? Because of constant volume process. So instead of V4, we can write in as a V1, okay, minus. So because already here we have a V1, so that I changed here also. Instead of V4, I am substituting as a V1. Because of constant volume process, the process between 1 and 4 is equal. P2 divided by R into P1 minus of 1. Again 1 divided by gamma minus 1. So here actually V1 is common, right? So here also we have a V1 term, here also we have a V1 term. So simply we can write V1 taking commonly outside, and rest will be a P4 into, again, P3 by P4. Already we are introducing a pressure ratio, right? See, pressure ratio is nothing but P3 by P2 or P4 divided by P1, right? Okay. Else, see here, P3 divided by P4 is nothing but R power gamma. So here, instead of P3 divided by P4, I can write as R power gamma divided by R minus 1, right? Minus of P1 into P2 divided by P1, right? So what is P2 divided by P1? P4 equal to P1, P2 equal to P3, right? So again, we can say, here itself, we can say P3 equal to P3, sorry, P2 and P4 equal to P1. So instead of P2 by P1, also we can write the same thing, R power gamma. So instead of P2 divided by P1, I can write or taken as R power gamma divided by R power R. Okay, and P1 divided by gamma minus 1. So here P4 into, if you go from numerator goes to the from denominator, if move on to the numerator, numerator means we can say as R power minus 1. So we can write like this, okay, P1. So here also same thing, R power gamma minus 1 minus 1. So here, now see, the term or which is common, right? So the remaining term is here V1 divided by R power gamma minus 1 into P4 minus P1 into R power gamma minus 1 minus of 1. Okay, and again we can, for simplification process, again we can write like this, from from this we can taking commonly outside as a P1. So remaining is a P4 divided by P1 minus 1, right? So taking commonly P1, so we can form like this equation into r power gamma minus 1 minus of 1, which is equal to again gamma minus 1 into see r power gamma minus 1 minus of 1. So here P1 instead of P4 by P1 we can say as pressure ratio, right? I hope all of you be remind. Already we solved the thing. Okay, and P1 V1 divided by gamma minus 1 into r power gamma minus 1 minus of 1 into rp minus 1. So this is equation number 8. So this is the work done calculation of an Otto cycle, right? So this is the simplified equation. In a problem, suppose asked to find out the work done of an Otto cycle means whether you can go for a simple equation, that is the uh, network done divided by heat supply. If network done is given and heat supplied is directly given to us, else the pressure volume parameter is given, you can go for this equation by measuring the combustion ratio and pressure ratio, right? So depend upon the whatever the conditions given in our problem, you can choose the formula for work done calculation, whether you go for a basic formula or a like this in terms of parametrical formulas. Okay. Okay. So see, next one more parameter we need to measure in an Otto cycle, that is mean effective pressure. Okay, the mean effective pressure is nothing but already we discussed in a basic concept class itself, right? Which is nothing but constant pressure acting on the piston during a working stroke. So generally we can use the formula mean effective pressure is nothing but work done to the shift volume, otherwise we can say as a stroke volume, right? So the formula is W divided by V1 minus V2, right? So this is the basic formula for mean effective pressure. So already we measured the work done calculation, right? Simplified equation. So we can substitute here, right? Instead of work done, right? Using the equation number 8. Okay, using the equation number 8. So in that the work done is P1 V1 divided by gamma minus 1 r power gamma minus 1 minus of 1 into OP minus 1. Okay, the whole thing divided by V minus 1, right? So here, again taking commonly outside V1, what will happen? The remaining is a 1 minus V2 divided by V1. Okay, So for the simplified form, again the numerator, please keep the same thing. Okay, V1 into 1 minus, already we know that compression ratio is nothing but V1 by V2, since we can use the term instead of V2 by V1 as a 1 divided by R. Okay, again simply taking LCM here, V1 into R minus 1 R minus 1 divided by R. Okay, say now P1 V1 into R power gamma minus 1 minus of 1 or P minus 1 divided by P1 into R minus 1 divided by R, actually here, right? So here you have one more term, right? So this is, so here you can say as gamma minus 1. So the from numerator, if goes here, means R power minus 1, R power minus 1 get cancelled. The remaining things like that V1 and V1 get cancelled. P1 into so if it goes here, means we can say as R power gamma minus 1 minus of 1 into or P minus 1, okay, divided by R minus 1 and gamma minus 1. So this is equation number 9. This is mean effective pressure, right? The mean effective pressure equation is the thing P1 or, okay. So likewise, if you go for a diesel cycle, again the same thing. You need to identify the basic efficiency formula of an OTTO cycle, and you need to derive a work done calculation and mean effective pressure. Right. I hope all of it get clear. How can you derive an equation of a efficiency, mean effective pressure, and work done calculation? Right. So okay, with this we will wind up this section. Okay, thank you to